Hello and welcome to part 8 of Dev Maths and Stats Refresher Course, Lecture 3. In this last part, I'm just going to look at describing features of functions using ideas related to partial differentiation. So, the main point of this is that you're quite likely, when you're reading articles and books, particularly quite technical material, that people will throw in these quite difficult sounding words like strictly increasing or quasi-convex or strictly concave, and it's useful if you understand what they mean. So I won't go through this very slowly. Just to point out, we're talking about functions of a single variable here. It's easy to generalize to multivariate functions, but it's just simple to show it on a two-dimensional graph. So to start off with, functions have to be strictly increasing if it's always sloping upwards, which you can say about a point or an interval or a whole domain. If it's not specified, it applies to the whole domain. If a function is flat in some areas but never actually goes downwards, then it's not strictly increasing. It's called non-decreasing. So strictly increasing also means there's no flat areas. Going the other way, you can talk about strictly decreasing and non-increasing functions. And the clear rule is that if the derivative is bigger than naught, then it must be strictly increasing. If it were greater or equal to naught, then it would be non-decreasing, and vice versa for strictly decreasing. Let's just have a couple of examples. 3 examples of that. So these 3 examples here, the first 2 are strictly increasing, always sloping upwards. So this is an example of one here where it's always sloping upwards because even at this central point, the point, even a microscopic distance afterwards is higher, and a microscopic distance before is lower, so it's sloping upwards everywhere. And this one is not. So the first 2 are strictly increasing. This is neither strictly increasing nor decreasing. If you look at the next one, this is one where it's increasing, but it's not strictly increasing because along here it's flat. But this one is non-decreasing. You don't often see increasing used on its own because it's not consistently defined. Some people do use it to mean the same as non-decreasing, but that's not well defined. If you want to say that it's it's either non-decreasing or non-increasing, in other words, it never changes direction, then the phrase is monotonic. So that says that it never changes direction and goes back on itself if it's monotonic. Next bit of jargon, a critical point is somewhere where you have a maximum, a minimum, or an inflection point, and that's whenever you get the gradient being 0. You can see that you've got some of these up here, so there's none there. Here we've got an inflection point where the gradient is 0. Here you have a maximum and minimum where the gradient is 0. And here you've got really an inflection point, an extended inflection point where the gradient is 0. If it's a local maximum, means it's bigger than all the points near to it. A global maximum means it's bigger than all the points in the whole domain. So you can hear here, this maximum is local but not global. This minimum is local but not global. Like monotonic, you can bundle those together into a single word, which extremum means either a maximum or a minimum is an extremum. If you draw this one, for example, here you've got an extremum here, it's a maximum, and it's a global maximum. It's bigger than any other points in the whole domain. As we've noted, anywhere you've got maximum or minimum, derivative must be 0. Okay, that's very, 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 very useful. However, it's necessary but not sufficient condition, because sometimes you can get something like this or this, where derivative is 0, first derivative is 0, but it's not an extremum, not a maximum or a minimum. So that's like a false alarm. So anyway you get an extremum, anyway you have an extremum, the derivative will be 0. And if this is seeming very easy to you, see if you can think of any exceptions to that, and let me know if there's any exception you can think of. But anyway the derivative of 0 doesn't have to be an extreme, like those two examples I showed you above, the false alarm ones. So the derivative being 0 is known as a first order condition. So you may have an extremum. There's other ways you can check it. And these ways are related to the shape of the graph. So you want to use derivatives to get at the shape of the graph. And that's what we do in the next few days. So the key words here are concave and convex. And concave is if it bends downwards from the tangent line, and concave is if it bends upwards. Just drawing, I just sketched it out a moment ago. Here's a curve. In this part of the curve, if this is a tangent line, it's bending downwards away from that, so it's concave. But here, if you draw a tangent line, it's bending upwards away from it, so it's convex. That's what's meant by that. A simple test is looking at the second derivative, and it's not easy to see why, but the idea is here that if you have some graph like this, if you take a tangent here, oops, then this is the gradient of the tangent. It's quite steep. As we move forwards this way, increasing the value of x or whatever the variable is, can you see that the slope has now decreased? So f dashed is decreasing. The slope is decreasing. So if you differentiate again, as we'll see, differentiating again tells you that the derivative is decreasing. The derivative tells you what the function is saying. So here the function is increasing, so that this derivative is positive, but the derivative itself is decreasing because here it's decreasing. Here the function is increasing less than it is here because it's becoming flatter and flatter and flatter. So f double dash would be less than 0 because f dashed is decreasing. And if this is decreasing, it means you must be in this kind of shape, which is a concave shape. So this gives you concavity. Okay. So, and similarly, if you do the reverse, if it's positive, it means that you've got convexity because the slope is getting steeper and steeper. So there's a way there of putting it together to make a test. We'll see that. We'll revise that again in the future. Another way of defining it is that if you draw a line, a line connecting 2 points on the graph, if it's always below the graph, then that's another way of saying you've got a concave graph. Can you see that? That's always below, so it's concave. And if that's true for anywhere, then it's called strictly concave. So this graph is concave here, but it's not strictly concave because this part goes convex. Okay. Finally, this kind of shape, this is just to show you that if you know that you have like this, a function, this is strictly concave, concave in the whole domain, that means that if you find a maximum, it must be a global maximum, which is good, but it's not strictly necessary to have this concavity everywhere. A weaker condition that still works is it's sort of almost concave, but you see these parts here are convex. This is called quasi-concavity or quasi-concavity, which means almost concave. So often in articles they say, I'm assuming this function is quasi-concave because they don't want to assume it's always concave everywhere, but at least it's got this kind of shape. So if they find a maximum, it's going to be a global maximum. And the way of defining the definition of this is that if you have any 2 points, if at point A the function is lower than it is at point B, then everywhere in between it must be higher than A. So if it's going up, it's never allowed to go down in between. And over here, if this is higher than this, it can never be lower in between. So it's almost like saying that on the left-hand side it's non-decreasing, on the right-hand side it's non-increasing. And that's bundled together by this way of defining it. So you might read those phrases, quasi-convexity, quasi-concavity, or strict quasi-concavity, meaning it's defined over the whole domain like that. Okay, so that's all of the bits of terminology I need to introduce there. So That brings us to the end of the lecture. I look forward to seeing you in the live session, but for now, thanks for watching. Bye.